All right, welcome back to the explainer. Let's be real, if you've ever watched your app server just completely choke and crash trying to process, say, a massive 5 GB video file, yeah, you know the absolute nightmare of file storage at scale. Today, we're diving into the ultimate reusable high-level design blueprint for enterprise SaaS storage architecture. We're going to break down exactly how the top-tier systems handle massive assets without breaking a single sweat.
So here's our roadmap for today. We'll start with a storage bottleneck, move into the decoupled system blueprint, trace the direct read and write workflows, then tackle scaling and data lineage, tenant isolation and resilience, and finally, wrap it up with the architect's mandate. All right, part one, the storage architecture bottleneck. Okay, so this image right here hits the nail on the head. It illustrates our absolute foundational rule, the decoupling axiom. Think about the classic anti-pattern for a second. Routing a massive file, like that 5 GB video, straight through your application server's memory is, well, it's like asking a regular person to bench press a boulder. It just doesn't work. You get these massive memory spikes, latency goes completely through the roof, and boom, your app crashes under the weight. The blueprint solution? Decoupling. You absolutely have to separate transactional metadata, stuff like permissions, file names, versions, from the actual binary storage. The app server should only ever touch lightweight JSON. Meanwhile, the heavy lifting, that massive video file goes straight to highly scalable object storage, like S3, Google Cloud Storage, or Azure Blob.
Now, if we lay out the architectural alternatives in a matrix, the fatal flaws of the old ways become pretty obvious. Storing big files directly in a database, or routing all that traffic through an app service. Yeah, that will literally implode at binary scale. The undeniable winner for SaaS storage is what we call the hybrid master pattern. By combining a transactional database for your metadata with direct, pre-signed URLs for those heavy binary uploads, it's just the perfect balance. You get strict transactional correctness right alongside infinite binary scalability. Which leads us to part two, the decoupled system blueprint. Take a look at this complete system architecture map. Notice that thin, lightweight path up at the top? The client connects to the API gateway and the storage API strictly for metadata operations. But follow that heavy path down at the bottom. The actual file bytes, they bypass the application layer entirely. The client talks directly to the CDN or object storage. You're completely saving your application from lifting those heavy binary weights. But to maintain this beautiful decoupled architecture, you've got to enforce strict component boundaries. And it's not just about what a component does own. It's about what it absolutely must not own. Take the storage API, for example. It owns upload orchestration, sure, but the anti-pattern, doing heavy inline file processing, don't do it. Your Metadata DB is your absolute source of truth for logical state, but you must never, ever store binary files in it. Enforcing these specific boundaries is exactly what keeps the entire system highly performant. Okay, let's zoom in a bit. Section 3, direct read and write workflows. Let's actually step through the primary write workflow, the happy path. Step 1, the client says, hey, I want to start an upload session. Step 2, the storage API jumps in, validates the user's auth and quota limits, and then creates this lightweight initiated record in the metadata database. Now here is where the magic happens. Step 3, the API hands back a pre-signed URL. This allows the client to upload the heavy binary directly to the object storage. Zero, and I mean zero application memory used. Then, step 4. Once the upload is done, the client calls back to say, all right, I'm finished. And finally, step 5, the API validates the file checksum, updates the database state to uploaded, and emits asynchronous events to kick off any background processing. And honestly, the read workflow is just as elegant. Step 1, the client wants a file, so they request a download URL. Step 2, the gateway safely forwards their tenant context. Step 3, the storage API checks the database. It asks, hey, does this user actually have permission to see this? If the answer is yes, we hit step 4, where it generates a highly secure short-lived signed CDN URL. And step 5, the client downloads the file at absolute lightning speed right from the edge network. Once again, the app server does no heavy lifting. Oh, and a quick aside here, if you're dealing with highly sensitive, maybe classified files, you can actually skip the CDN entirely and route that specific download through a controlled proxy, so you always maintain that granular control. Now, as files move through those workflows, the object's state machine is constantly evolving. It starts at initiated when the session kicks off, right? Then it moves to uploaded when that direct put finishes. Maybe it shifts to scanning for background virus checks. And finally, it settles at active, or, eventually archived or deleted. But here's the catch. Tracking this state safely over unreliable networks requires a pretty serious architectural shield.
That brings us to Section 4, Scaling and Data Lineage. And that shield? It's idempotency. Honestly, I cannot stress this concept enough. Look, networks are flaky. Clients are going to retry their upload complete calls. It happens. If your system isn't idempotent, a random retry might accidentally create a duplicate object, or worse, corrupt your database. So by enforcing a strict, unique database constraint, using a combination of the tenant ID, the object ID, and the version ID, you are basically building an impenetrable fortress. It guarantees that no matter how many times an async worker or a client retries an operation, your final state remains perfectly 100% consistent.
Speaking of consistency, we really have to draw a hard line in our data lineage. It's truth versus derived state. Your locked-down, top-tier source of truth, that's your object metadata. The version pointer, the actual binary sitting in storage, and your audit events. That stuff is sacred. Everything downstream from that, we're talking OCR text extractions, thumbnails, search index documents, cache entries, that is all fluid, derived state. So if a search index randomly gets corrupted, you don't panic. You just calmly rebuild it from your top-tier immutable source. Now, to build all those thumbnails and search indexes without dragging down your main upload speeds, we rely heavily on async queues. But heads up, not all queues are created equal. For state-sensitive streams, like updating a piece of metadata or deleting a file, you absolutely must use strict ordering. You partition that by the object ID so events happen in the exact precise sequence they occurred. On the flip side, for heavy processing streams like generating 3 different thumbnail sizes or video renditions, you want maximum parallelism. Partition those by a job ID so those heavy tasks can fan out and process independently at massive scale. And here's a crazy thought. A tiny naming decision can literally crash your entire storage at scale. The deadly anti-pattern here is using sequential object keys. If you name your files, object 1, object 2, object 3, you are hammering the exact same storage partition in the cloud. You're creating a massive hotspot. Under a heavy enterprise workload, yeah, it will fail. The industry best practice is distributed keys. If you use a formula like the tenant ID plus a hash of the object ID, it perfectly distributes that input-output load across multiple storage shards. This keeps your performance blazing fast while maintaining strict tenant isolation. All right, Section 5, Tenant Isolation and Resilience. When you are building for enterprise SaaS, the absolute golden rule is this: never, ever query only by the object ID. This is defense in depth in action. Tenant scoping has to be rigorously enforced at every single layer of your stack. Down in the data layer, the tenant ID is mandatory in every SQL query. In the storage layer, it acts as the root prefix in your object keys. Even your async events and cache keys have to be strictly scoped. If you bake the tenant ID into every layer by default, cross-tenant data leaks become virtually impossible. But what happens when things actually go down? Because let's face it, they absolutely will. Welcome to software engineering. This is where graceful degradation saves your life. If your search index goes offline, the whole system doesn't crash. Core uploads and downloads still work perfectly fine. Your UI just shows temporarily stale search results. If the thumbnail worker dies, the system seamlessly degrades to showing generic file icons. If the quota service is unreachable, you fail securely. Block massive new uploads to protect your storage, but keep reads available so users can still get to their data. And if the CDN totally drops, you instantly fall back to serving signed URLs directly from the object store. No matter what secondary systems catch fire, your core functionality survives. Finally, Section 6, the Architect's Mandate. So let's wrap this up with the Architect's Mandate. These are 4 non-negotiable rules to take back to your engineering teams right now. 1. Separate concerns. Let the database handle the logic, and let object storage handle the massive binaries. Everything else is derived. 2. Bypass the middleman. Never route heavy files through your application memory. Use those pre-signed URLs. 3. Decouple via events. Keep your critical upload path lightning fast and offload all the heavy lifting to async queues. And 4. Isolate by default. Make sure that tenant ID exists at every single layer of your infrastructure. So take a hard look at your own legacy data pipelines today. Honestly, which of these 4 rules is your system currently breaking? And how quickly can you start implementing this blueprint to fix it? Thanks so much for joining me on this explainer, and I'll catch you in the next one.